Large language models now process entire books and code bases in a single prompt. These systems are routinely tasked with handling millions of tokens simultaneously. To retain this context, the model converts every token into a high-dimensional vector, a mathematical coordinate representing its meaning, and stores it in the key value or KV cache. But physical hardware imposes a hard limit. High bandwidth memory, or HBM, is finite. Moving these massive blocks of data between storage and computation creates a communication bottleneck that throttles inference speeds. To maintain performance, engineers must compress these vectors. The objective is to shrink 32-bit floating point numbers down to as little as 3 bits per coordinate. The primary tool for this is vector quantization, which maps a vast continuous space of values down to a small set of discrete integers. Standard vector quantization requires a custom codebook to decode the data. This introduces significant memory overhead, extra bits stored just to read the compressed values, which can negate the efficiency gains of the compression itself. This creates a context window wall, where the demand for deep memory is trapped by the physical limits of hardware storage. Researchers at Google have demonstrated an algorithm named TurboQuant that achieves 4 to 6 times compression with zero measurable loss in model quality. In needle-in-a-haystack tests, where a model must find one specific fact in a massive document, TurboQuant maintains 100% recall accuracy up to 104,000 tokens. Its performance line perfectly overlaps with uncompressed, full-precision data. This contrasts with leading token-level compression methods like SnapKV. At identical context depths, SnapKV's recall drops sharply after 16,000 tokens, failing to retrieve the hidden data. This is a mathematically lossy compression that produces results indistinguishable from a lossless system. Discarding 90% of a vector's data usually destroys the signal, yet in these tests, the model's ability to reason remains intact. Standard engineering pipelines optimize for data error in a way that ignores the specific geometric requirements of a transformer model. TurboQuant's efficacy suggests that the current limitations of context depth are not physical, but are instead a result of how we structure data-oblivious compression. Most compression methods require analyzing the dataset first to build a custom codebook, an overhead trap that consumes both time and memory. This is impossible for LLMs, where the cache is generated and stored in real time as the model predicts the next token. TurboQuant bypasses this using a data-oblivious approach. It begins by multiplying the input vector by a random rotation matrix, denoted as pi. This rotation forces every coordinate in the vector to follow a predictable beta distribution, regardless of the coordinate's original value. In high dimensions, coordinates become nearly independent and converge toward a specific, known concentration of measure. Because this distribution is fixed and predictable, the system uses a pre-calculated Lloyd-Max scalar quantizer. Each part of the vector can be quantized individually, instantly, and with zero prior knowledge of the overall dataset. This removes the requirement to store expensive quantizing constants or lookup tables for every block of data. By intentionally randomizing the input, the data is forced into a geometric shape perfectly suited for high-speed compression. These scalar quantizers are typically built to minimize mean squared error, or MSE. MSE focuses on the L2 norm, the literal physical distance between the original high-precision coordinate and its quantized approximation. But transformers do not prioritize distance. They use inner products, or dot products, to calculate attention scores. A quantizer optimized strictly for distance inherently introduces a systemic bias into inner products. These histograms show the error distribution for 1-bit and 2-bit results shifted away from the zero axis. This bias means the quantization drifts the vector's angle. Even if the distance error is low, the warped angle produces a hallucinated attention score. At 1-bit precision, this systemic bias is exactly 2 over pi, a massive distortion for a model attempting to weight information. The model believes it is paying attention to the correct tokens, but the underlying math is skewed. Correcting this requires a secondary architecture designed to function as a mathematical corrector. This is the paradox of error. Being highly accurate in distance can make a system systemically wrong in similarity. TurboQuant addresses this bias by dividing the quantization process into 2 parallel stages. First, the system applies an MSE-optimized quantizer, using 1 bit less than the total budget. In a 3-bit setup, this stage uses 2 bits. This captures the bulk of the vector's information, while leaving a small, measurable remainder. This is the residual error, the precise difference between the original vector and its 2-bit approximation. The second stage applies the Quantized Johnson-Lindenstrauss, or QJL, transform strictly to that residual error. QJL uses a random projection to map the error to a single binary sign, either +1 or -1. QJL is a mathematically unbiased estimator. Adding this 1-bit residual back to the MSE result cancels out the inner product bias. This produces an expected inner product perfectly equal to the original full precision value. The QJL stage is a zero overhead operation that adds virtually no measurable latency to the inference process. By dedicating a single bit to this error correction, TurboQuant achieves an unbiased attention mechanism at a fraction of the memory cost. Claude Shannon, the architect of information theory, established the absolute mathematical limit for how much data can be compressed before the signal is lost. The Shannon lower bound represents the theoretical ceiling, the best achievable distortion rate for any possible compression algorithm. This logarithmic plot compares TurboQuant's actual distortion curve against Shannon's theoretical limit. Across all bit widths and dimensions, TurboQuant tracks within a factor of only 2.7 of the absolute information theoretical limit. Because the algorithm is data-oblivious, it drastically reduces the time required to build searchable vector indices. Product quantization requires 239 seconds to index a high-dimensional dataset. TurboQuant accomplishes the same task in 0.0013 seconds. This makes pure online quantization viable in real time, allowing models to compress massive code bases and entire libraries as they are being read. TurboQuant demonstrates that by utilizing the geometry of high-dimensional space, AI efficiency can be pushed to the edge of what is mathematically possible.